Test 1, 2, 3. Good.
Hello, everyone. Welcome to this session 1D, attacks on mitigations. Um, for the first talk, we have Anish Anish Saxena will be talking to us about his work on Rubix, which is reducing the overhead of secure Rowhammer mitigations via randomized line-to-row mapping. Just a few logistics. Each talk is 12 minutes with 3 minutes of Q&A. If you have any questions in the audience, you can raise your hand and I'll bring the mic to you so you can ask the questions. Yeah. So some words about Anish. He's a third-year PhD student at Georgia Tech, advised by Professor Moinuddin Qureshi. His interests include hardware security, data center memory systems, and system design for LLMs. His recent works on Rowhammer defenses have been published in leading venues like Micro, HPC, and ASPLOS. He has also worked on designing servers that leverage CXL. Most recently, Anish has been exploring optimizations to improve LLM serving, a topic he will be working on while interning at NVIDIA Research this summer. Previously, Anish has interned at Intel Labs, Micron Research, and AMD Research. Anish is an Aditya Birla Group scholar and has received his bachelor's from IIT Kanpur from India.
Thanks for the introduction, Moumita. Thanks. Hi, everyone. I am Anish Saxena, and I'm excited to present our work on randomized memory mappings for low overhead and secure Rowhammer mitigations. So this work has been done in collaboration with Saurav and my advisor, Professor Moin Qureshi at Georgia Tech. So let's get started. Rowhammer is a hardware vulnerability where frequently activating an aggressor causes bit flips in nearby victim rows. Rowhammer is not just a reliability concern, but a severe security threat that can break confidentiality and privilege boundaries. Typical solutions for Rowhammer consist of two parts: tracking activations to a row and performing a mitigative action once the aggressor reaches a threshold of activations. The typical mitigative action involves refreshing the victim rows to prevent Rowhammer, and this is a commercially deployed mitigation and can be found in DDR4 modules. One problem of victim refresh is that it maintains the spatial proximity between the aggressors and victims, giving the attacker ample time to craft complex attack patterns. For example, the half-double attack from Google leverages victim refresh itself to cause an attack. It induces so many victim refreshes in the nearby rows that it causes bit flips in neighbors that are a distance of 2 away. So this attack breaks out commercial and proposed mitigations that rely on victim refresh. So recent proposals have developed mitigative actions that are resilient to such complex patterns by focusing on the aggressor instead of the victims. A prior work of mine, Aqua, moves the aggressor away from the victim's neighborhood by migrating the aggressor to a dedicated quarantine region of memory. Another recent work, which is scalable row swap, swaps the aggressor with a randomly selected row in memory. Finally, Blockhammer controls the access rate to frequently activated rows, and by ensuring that no row gets more than the threshold of activations within 64 milliseconds, it also prevents complex attacks. So these mitigations are secure, but incur higher latency because they are complex compared to victim refresh. And because row migration, and this is because row migration schemes like Aqua move kilobyte size rows, while rate control in Blockhammer delays accesses by several microseconds or maybe even more. So at near-term threshold of 1,000, mitigative actions are there, and the overhead of these schemes is low. Unfortunately, the Rowhammer threshold has reduced by over 30 times in a span of just 6 years to just 4,800 activations. If this trend is to hold, we will see ultra-low thresholds of a few hundreds or less by the end of this decade. At such ultra-low thresholds, the problem becomes much worse. At a threshold of 128, Aqua's overhead increase to 15%. SRS incurs a drastic slowdown of 60%, and Blockhammer is completely unusable with a 600% average slowdown. So the goal of our work is to make these schemes viable even at an ultra-low threshold of 128. So far we have seen that secure mitigations become impractical at ultra-low thresholds. Now let's see what the problem is and how we can solve it. So the reason for high overheads is that the number of rows that require mitigations, which we call hot rows, increase as the threshold reduces. At a threshold of 1,000, there are only about 200 hot rows on average within a span of 64 milliseconds. However, at a threshold of 128, the hot rows increase to almost 10,000 on average, and this 50-fold increase in hot rows causes frequent mitigations because they are complex and leads to high slowdown. So why do we have hot rows is the question we tackle. So I would argue that hot rows are not the norm but the exception. So consider a bank with around 128,000 rows. The budget is approximately 1.4 million activations within 64 milliseconds. So even if the bank is hammered continuously, the average activation count would be around 10. And if these activations are equally distributed, then we wouldn't see any hot rows at all. And even if the activation pattern is random, only a handful of rows will see 20 or more activations, far away from the threshold of 128. So clearly, thousands of hot rows shouldn't really exist. And clearly, the activation pattern is neither random nor equal. So why is this the case? A DRAM row comprises of around 128 cache lines. And the activation count to a row is the sum of the activations to all of these 128 lines. So it is unlikely for just one or a few of these lines to incur hundreds of activations because such lines are typically cached, right? So instead, many lines within the row incur only a few activations each. And let's look at the cache line to row mapping policy to see why this happens. You can place a 64 kilobyte page comprising of 64 lines in the same row buffer to maximize row buffer hits, right? But you can leverage bank level parallelism by distributing portions of this page to different banks. And this is done in the Intel Skylake mapping that we have studied. So 32 lines from a page reside within the same DRAM row. And crucially, each of these lines can contribute to the activation count of the row if the page is accessed, if this page is accessed. So this portion of the page alone within the bank gives 32 opportunities to activate lines that are spatially proximate. And the problem is even worse because multiple portions of physically contiguous pages or proximate pages are put in the same row to further increase locality. And if these pages are hot, we can greatly increase activations to this row. So let's see how this plays out, right, with a toy example. We will track the activations that happen to each row within this single bank that is shown here. And let's just add two vectors A and B and store its result in vector C. To fetch portions of vector A, we will incur some activations and we will do the same for vectors B and C. See, if we access lines in a row, all lines in a row within a span of a few hundred nanoseconds, then almost all of these accesses would actually be row buffer hits. But typically accesses are interleaved and accesses to the same row can be spaced out by microseconds or even milliseconds. And by that time, the row buffer closes and we will incur row activations even for spatially proximate lines. So this keeps happening, and notice that these activations are limited to only a few rows. So as we progress, these few rows become hot rows while other rows have no activations at all. And this is not the patterns that we expected before, right? So the root cause of episodes of hot rows is the memory mapping, which places spatially proximate lines within the same DRAM row. And when these spatially local pages that are mapped to this row get accessed, the row encounters many activations, which make it a hot row. So wouldn't it be nice to distribute these activations more evenly to all rows in memory? That way, it would be very unlikely for a given row to accumulate many activations. This is the key insight of our work. By randomizing the set of lines that co-reside within the rows in memory, we can break the spatial proximity between lines mapping to a row. So activations to physically proximate pages get scattered to all rows in memory, resulting in virtually no hot rows. And using this key insight, we developed our randomized memory mapping, which is Rubix. So let's see how we do this. Consider 4 lines that would co-reside within the same row with a conventional mapping, like the Skylake mapping that we saw. So we place a cipher at the memory controller to produce an encrypted line address for each channel. With this encryption, these 4 lines get scattered to different rows, breaking the spatial proximity between the lines that coincide within the row. So we use this K cipher in Rubix. It is a programmable bit-width cipher, and it can adapt to varying memory capacity within the channel. We call our design Rubix S because it randomizes the line locations statically. As you might imagine, if we randomize each line address, then the 128 lines that reside within the row are random. And this would give us virtually no number of hits, and it will impact performance. So to prevent this, we can encrypt a group of, let's say, 2 lines, which will give us up to 50% group of hits. More generally, we can have a group of 2 to the power of k lines. And for an n-bit line address, the group address is just the top n minus k bits. Randomizing the group address preserves the spatial locality of lines that belong in a group, which aids group of hits. But different groups within the row are still randomized, preserving the property of randomization property of Rubix, as we see here. So compared to typical memory mappings, Rubix reduces hot rows dramatically, right? On the left, there are almost 10,000 hot rows on average for these conventional mappings. And at a group size of 1, Rubix has virtually no hot rows. These are empirical results. Even for a group size of 2 or 4 lines, there are only a few tens of hot rows on average. This is a reduction of 2 to 3 orders of magnitude in the number of hot rows. And as mitigations are now invoked much less, the performance overhead of Rubix mapping is negligible. With Aqua, SRS, and Rowhammer, we have a performance overhead of about 1 to 3% in average. And because we only require a register to store the 96-bit key for the K cipher, we will have a SRAM overhead of just 16 bytes, which is negligible. And as each system also has a different key, the resultant randomized mapping will also differ from system to system. Finally, but importantly, Rubix is just a memory mapping. So it retains all of the security properties of the underlying Rowhammer mitigation like Aqua or Blockhammer. So as you can see here, the group level randomization retains robust hit rate of about 40% compared to 60% for the conventional policies. And the slowdown due to the mapping alone, even if we don't have any mitigations, underlying mitigations, it's just 1% for a group size of 4. Even for a line level randomization, it is about 2.6 to 3%. We have several more sensitivity studies and discussions in the paper. So we have power overheads, memory intensive workloads, and so on. We also have several other designs that break the spatial proximity between the lines that reside within a row in the paper. So we have Rubix S, right, which is static randomization. So naturally, we also have a dynamic randomization scheme, which is Rubix D, and it has some nice properties. So I refer you to the paper for the details. So to conclude, right, in the face of plummeting Rowhammer threshold and complex attack patterns, we need secure mitigations to scale to ultra-low thresholds that we will likely see in the future. They don't currently work for ultra-low threshold because the root cause of mitigations, which are hot rows, increase dramatically as the threshold reduces. So we reduce these episodes of hot rows by breaking the spatial correlation between the lines that map to a row. We have presented the static randomization scheme. There is also a dynamic flavor of it, and our design is called Rubix. It makes secure mitigations viable at ultra-low cost with just a few SRAM, bytes of SRAM and negligible power, performance overhead. So That's Rubix. Thank you for listening, and I'm happy to take questions now.
Any questions?
Thank you very much for great work, very great presentation as well. So out of curiosity, I'd like to ask, so do you think this kind of changing, randomizing the lines to row, this would accelerate or I'd say improve many-sided Rowhammer attacks?
It will not, so most all of this work is for benign applications. You can still hammer the same row by just accessing the same cache line again and again, right? But because we have secure mitigations in place, the Rowhammer attack will not be successful. So you will not incur bit flips. You can still cause slowdown as an attack or malicious party, but you will not have bit flips.
Thank you very much.
Any more questions? Okay, I can ask the question. So I believe like you have more information about that in your paper, but this is something pertaining to power overheads. When you have a highly streaming application, which really leverages the row buffer hits, when you randomize and keep these different pages in different rows, that would increase the power overhead in addition to the performance penalty. So can you comment on how like what would be the effect for especially students?
Yes, that's a good question, right? So there are two aspects to it. One is at higher band sizes or group sizes, the impact on buffer hit rate is lower, right? So the performance and power overhead would be lower. Now the question is, why would the power overhead be lower? Activations are only a small portion of the overall DRAM power. There is the static DRAM power, there is the idle DRAM power, right? If 10% of your power is attributed to activations, even if I double the activations, your power overhead will only increase by 10%, right? Or 20%, something like that. So the power overhead does not increase by that much. I also have streaming workload results. It's mostly the performance that is impacted, which is approximately 7-8% overhead, because as you said, it leverages row buffer hit rates quite a bit. So this is for stream benchmarks, adding two vectors and so on, copying two vectors.
Thank you. So follow up on that. Will the randomization in certain cases also increase your bank conflicts?
It won't increase we didn't look at band conflicts necessarily. It is done at a channel level. So for some banks it could, but I would say that randomization would make it more uniform, the activation pattern. So I don't expect it, but we have not measured inter-band conflicts, like band conflicts essentially.
Questions? Thanks, Anish, for this great talk.
Thank you. Thanks, everyone.
For the next talk, this is on Tarot, a CXL SmartNIC-based defense against multi-bit errors by Rowhammer attacks. To present this work, we have Chihun Song.
Right.
A small introduction on Chihun. He is currently pursuing a PhD degree in ECE at the University of Illinois at Urbana-Champaign. His current research interest is system for memory security. Whenever you're ready.
Thank you. Hello, everyone. My name is Chihun from University of Illinois at Urbana-Champaign. Okay, I represent our recent work titled a CXL SmartNIC-based defense against the multi-bit errors by Rowhammer attacks. This is a collaboration between Qureshi and Seoul National University. Rowhammer is well-known significant security risk in modern DRAM-based memory systems. By repeatedly accessing the DRAM rows, Rowhammer can flip the neighbor bits, and it can crash the system with multi-bit uncorrectable errors. System-level Rowhammer defense, such as refresh rate control and error correction code, cannot provide full protection from the Rowhammer attacks. For example, the ECC for DRAM is single-bit error correction and double-bit error detection code. Our proposed software-based Rowhammer mitigation solution employs the CXL protocol. The CXL interface was introduced in 2019. In a high level, it uses the high-speed and low-latency PCI Express link, but provides a rich set of features, including CXL.cache for device-to-host cache coherence and CXL.mem for host-to-device cacheable memory access. Compared to PCI Express-based SmartNIC, CXL-based SmartNIC can potentially offer unprecedented efficiency and capability by efficiently accessing the host memory space. This paper is the first work to harness the CXL-based SmartNIC for Rowhammer mitigation with CXL.cache feature. In this paper, we used two evaluation systems, Intel Xeon E5 CPU-based server and a DDR4 adapted FPGA. We evaluated 17 DDR4 DRAM modules from 3 different manufacturers between 2016 and 2023. We tested the characteristics of Rowhammer-induced bit-flips errors, employing many-sided Rowhammering with low-stripe data pattern. The number of hammerings in a round is based on the maximum number of activations within a single refresh window, and after each round of Rowhammering, we checked every bit to record their row and column addresses for 3 weeks. We collected the number of bit flips for every cell in a bank over 3 weeks and plotted them in a bit flip heat map. This shows that some bits are far more frequently flipped than others. That means some cells are more vulnerable to Rowhammering. Meanwhile, 99.99% of the bits have not flipped even after conducting the Rowhammering experiment for 3 weeks. That is, Rowhammer vulnerability is caused by manufacturing process variation within a chip. The following figure demonstrates that the number of Rowhammer-induced bit flips significantly varies across different banks within a chip, as well as across different chips within a module. For example, chip 3 gives 3.4 times more Rowhammer-induced bit flips than chip 7. Also, within a chip 6, Bank 3 gives 2.3 times more Rowhammer-induced bit flips than Bank 2. We see that such Rowhammer vulnerability comes from manufacturing process variation not only across banks within a chip, but also across chips within a module. After 3 weeks of experiments, we uncovered that Rowhammer-induced uncorrectable errors occur as specific DRAM addresses. We also demonstrated that the number of these vulnerable addresses accounts for only a small fraction of the overall DRAM addresses. This figure shows the Rowhammer-induced uncorrectable error rate for 3 weeks. Over the iterations, we identified the uncorrectable errors by combining correctable errors from different iterations. We observed that the number of unique uncorrectable errors in 3 modules converged to very small percentage. The remaining 14 modules did not present uncorrectable errors. That is, only small number of specific DRAM addresses exhibit uncorrectable errors under Rowhammering. Also, we expanded the data set of hardware modules. After taking the Rowhammer-induced bit flip addresses from 80 chips across 7 modules, we constructed 1024 virtual module. We consider each chip as an independent random variable. The figure on the right presents the distribution of the number of unique Rowhammer-induced uncorrectable errors from these virtual modules. They show that the +4 sigma value represents only 0.05%. Based on this empirical analysis, we assume that there are 1,000 vulnerable rows in a 16 GB DRAM module for the last evaluation. Based on these observations, we propose targeted Rowhammer therapies, which we abbreviate as TART. Also, we propose to store the vulnerable addresses in the serial presence detection chip placed on every module. The first module, HTAR, is designed to run on the host CPU. HTAR periodically refreshes the vulnerable addresses by flushing and reading the cache lines of the target addresses using host CPU cycles. During the system bootup, HTAR obtains the Rowhammer uncrypted vulnerable addresses from the SPD chips in the module. HTAR is activated periodically to flush the corresponding cache lines, and then it accesses the DRAM to refresh the vulnerable row addresses. However, as DRAM technology scales and DRAM capacity grows, HTAR should access more addresses within a given refresh period. So, to tackle this challenge, we propose to offload the HTAR from the host server to the SmartNIC in the second module as TAROT. However, conventional PCI Express-based SmartNIC cannot activate target row if the corresponding cache line is in the host CPU. For example, PCI Express-based SmartNIC can access addresses in the host memory space through the kernel space RDMA. However, it ends up accessing the corresponding cache lines in the host CPU. We propose to use the CXL-based SmartNIC for STAROT. We employ a unique capability of future CXL-based SmartNIC, which can flush and read the data cached in the host CPU. Thanks to cache current interconnect to the host CPU, the CXL SmartNIC can access any addresses in the host memory space. Since CXL-based SmartNIC is not available yet, we emulate the CXL-based SmartNIC using one of the newer nodes in a stereo-scale system. Furthermore, expecting that the SmartNIC CPU serves as the control plane for the network interface or other accelerators such as GPU, we hypothesize that the SmartNIC CPU is underutilized. For example, we observed that only 5 SmartNIC CPU cores are required to accomplish the maximum accelerator throughput on the fully stress of the SmartNIC accelerator. That is, among the 8 cores of SmartNIC CPU, 3 cores are not used. This is the first work that explores the potential use case of CXL-based SmartNIC for Rowhammer defense. By offloading power from the host CPU to the SmartNIC CPU, we can minimize the performance penalty on the host CPU. We see 5% increase in the execution time for HTAR when system use 512 GB DRAM. We also see 120% increase in the 99th percentile latency increase for HTAR when system use 512 GB DRAM. Meanwhile, HTAR shows a negligible performance penalty for the both applications. HTAR can reduce 95% of the execution time increase and 98% of tail latency increase, respectively. The result of 2 graphs shows that the interference of HTAR on the host CPU is very small. When we compare the power with prior works, HTAR shows the best performance on the host server, while prior work consumes the DRAM bandwidth for increased refresh operations or spans CPU cycles for expensive address sampling or migrates pages of Rowhammer attack detection. How simply refresh the target addresses. In summary, as title shows the negligible performance penalty on the host server. Tarot is better than fireworks for the protection scope, performance penalty, physical memory fragmentation, and kernel modification. For the protection scope, Tarot can access any low addresses of the DRAM. Meanwhile, fireworks using page migration cannot protect between rows serving unmovable pages from Rowhammer, since such pages cannot be migrated and offlined. Lastly, page isolation and page offline incur physical address fragmentation, and it decreases the number of available huge pages. To conclude, in this work, we observed that some cells are more vulnerable to Rowhammer, and Rowhammer vulnerability varies within a chip and across chips. Furthermore, uncorrectable errors occur only at specific addresses, and the number of such low addresses is very small. Based on these observations, we propose 6-based SmartNIC-based target row refresh, and this is the first work to harness the 6L protocol for Rowhammer defense. Thank you very much.
Hi, Moin. Hello. I'm Qureshi George Beck. Nice talk. Couple of questions. First, who characterizes, is it the DRAM manufacturer or the user who characterizes the severity of which rows are vulnerable or not? And how is this information stored?
Oh, yeah.
Yeah.
Can I answer?
Yeah,
first?
go ahead.
Yeah, so good question. So in the town, the problem is how to identify the vulnerable addresses in the DRAM. So as we know, the manufacturer we are manufacturers we are collaborating have advanced the method to identify the Rowhammer vulnerable cells, but the problem is the number of Rowhammer vulnerable cells is too many. So that means it's impossible to repair all the cell. So I think that this tau can be used in this case.
So there is some non-volatile memory on the DIMM that stores the characterization data when the DIMM is shipped.
So we propose to store this vulnerable address in the SPD chip, the serial presentation chip. So I think we believe that in the SPD chip we can sufficiently store the vulnerable addresses.
In some form of non-volatile memory, right? Second, does the behavior of Rowhammer bit flips change over time with temperature, with voltage? Are there scenarios where a row that you thought was not vulnerable becomes vulnerable?
Yes, that's a good question. Yeah. So as you said, the Rowhammer vulnerability is depend on the temperature and voltage, right? So our paper targeted server-based system. So we believe the server temperature is very narrow range, and then we tested the Rowhammer vulnerability on the temperature, and then it showed that the testing of the single temperature cannot provide the superset of Rowhammer vulnerability. So, however, in this evaluation, we see that the total number of Rowhammer vulnerable cells are very small. So I think we can use this our proposed solution.
Thank you.
Hey, Daniel Genkin, George Tech. Great work. I was curious about the slide you show when you tested it on the Xeon server. How did you reverse engineer the row bit addressing functions? Into individual DRAM rows.
So the how to reverse engineer the row mapping.
Yeah.
Yeah. So from the virtual address to physical address, right? So
say again.
So how to reverse engineer
row mapping from physical address to on-DIMM mapping.
Yeah, right. So Based on our Jeong server, we used just only one DIM population. So Fireworks provide some reverse engineering method. So measure the time difference between from the bank company. So we use the previous work.
Yeah, but that won't tell you the distance between DIMs.
Yeah.
So bank conflicts tells you if two rows collide into the same bank. That's basically drama. But what happens if, how do you know the distance between rows? Because you're gonna do double-sided number.
Yeah.
You can take it offline.
Yeah.
Take it offline.
Yeah. Just keep moving, let's leave the other questions for offline discussion. So, thank you, Chihun, for this very interesting work. Next we have, PyThia, which is a compiler-guided defense against non-actual data attacks. To present this work, we have Sharjit Khan. He's a last year computer science PhD student at Georgia Tech, working with Dr. Santosh Pandey. His research interests lie in intersection of programming languages, security, and compiler research. His work uses compiler program analysis to improve software verification techniques and solve security problems.
Thank you so much, Moumita. Hi, my name is Sharjit. I'm a PhD student at Georgia Tech. With my collaborators, Bodhi and advised under Dr. Santosh Pandey, I'm here to present PyThia, compiler-guided defense against non-controlled data attacks. So applications written in memory unsafe languages like C and C++ are vulnerable to data attacks. And one example of that is non-control. And this can lead to privilege escalation, they can lead to arbitrary code execution. So the idea is that these attacks are very important. One particular case of this is called control for bending. Basically, you corrupt a branch variable, or a variable indirectly corrupts the branch variable, and basically can lead the branch to an unwanted target part. The issue is that defending against them have different cases. The issue that too many branches in a program, or there are too many pointers which can affect a branch. So we did a case analysis on spec and Nginx. And so what we noticed is that over 50% of the branches in spec and Nginx are conditionals. And then so it's a very scalable problem you need to think about for in a technique. At the same time, we are around 200,000 pointers which affect the branches. So you need to think about how your technique can analyze these pointers information. So we do have some examples. This is a very simple example of a pointer corruption. Basically, p stores the address of array. If you look at the stack, k is if you overflow k, you can change the pointer value of p. And basically, p will point to m now, and you can just add 1, and it will basically execute the if condition block. So here, pointer p can be routed by k due to overflow. In this more bigger example, what you can see here exactly is that there's some input string called some input. You have a first string comparison after verifying with username. Now, when you do the str copy, what you notice is that str and some input have different sizes. So if the str size is bigger, when you're copying it over, it will overflow into user based on the stack. And so when you do the second str and compare, it can become true. And it can actually, buffer overflow, cause super user privileges. Now, these attacks have been very, very well known the last few years, and a bunch of techniques have tried to go against it. One example is DFI. It handles control for bending by checking reachability constraints at runtime. But the one issue is that it has high overheads, around 40% to 100%. It's incompatible with some C++ branches, basically landing pad stuff. And in the paper, they make some assumptions about conservative pointer metric, which they don't take into account. Another case is randomization. Basically, you try to do some random relayout for both stack and heap. But if you do it at runtime, it causes high overheads, and static randomization has been shown to be not that effective. And they either are specific to stack or heap. The more complete solution is memory safety, which introduces the non-trivial language extensions to prevent both spatial and temporal memory violations. But all techniques nowadays have very significant overheads because they try to take care of all cases. And we have some of these memory safety papers have issues now with C++ benchmarks. So the idea is that the two main issues is high overheads And or another idea is that they're not very packed. They might have some issue with C++ benchmarks or pointers. So in our scheme, we wanted to do something with low overheads, and we wanted to look at something at the hardware. So you want to utilize something like ARM-PA. So ARM pointer authentication is a specialized hardware mechanism that ensures integrity of data and code pointers. The reason why is because not all bits are needed in the point. Not all bits are needed for a pointer. So the top bits could be used for something as a pointer authentication code. So in the 64-bit architectures, you need only at most 40 bits, and the rest can be used by pack. So if you want to guess the pack, you need a 1 in 16 million chance. So if you look at this, this is actually how it happens. You have a secret key, which is defined in hardware. You have your pointer, and you have a modifier. And in our case, what we're going to use is the value at the pointer as part of the modifier. So when you're encrypting the pointer with a value, if the value goes off, if it gets changed, it means that when you decrypt it, it'll crash the program, and you know something's wrong. Each of these decryptions are actually in 2 nanoseconds, so they're quite fast. So the first idea is that let's do a baseline idea, right? Basically, all possible program vulnerabilities that can affect the branches, let's just encrypt, decrypt them, right? And the question is, how do you detect all these branch pointers and variables? So we do some compare analysis to figure that out, and we encrypt and decrypt them along the way with ARM-PA. So for any given branch, we traverse the variables, use def chains, and detect all variables affecting the branch. So for example, in this example, you have an if condition and a while condition, which will become branches. And so E, F, and G are particular variables you need to look at. And so you backslash E, you get A and B. You backslash F, you get C and D. You backslash G, you get A and B. Basically, this is also the case of aliasing. If you encrypt the pointer, you need to make sure all these aliases are also like taken care of if they change the value. So we also have to find all the alias and alias cases also. Now, what we typically do is that we authenticate pointers when they're loading from memory, and we encrypt them when they're storing the memory. The reason why is that if you want to register the pointer in the register, we don't expect you to overflow that value. And this allows us to reduce the number of encryptions also. Of course, you need to do one encryption at the very beginning when the pointer was created or the variables first used, but that's of course a necessary case. Now, here's the same example we had before. What we notice here is that we have an if condition here, a backslash to the user. Here also this one backslash to the user. So we sign it, basically encrypting the pointer. When we use a user, we authenticated it here and here. Now, if user was in the register the entire time, you wouldn't need the second authentication, but that's in case for this case, we're showing it to you. Now, if we do this for every single pointer and every single branch, what we notice is that we get about 48% overhead. So that's a lot of pointers, that's a lot of variables necessary, and actually blows the binary size by 22%. The question is, what can we do to reduce this overhead, right? And the idea we saw that we noticed something is that we have to do 2 kind of variables, right? Stacks and statically allocated variables and dynamically allocated variables. So we basically defined 2 memory space layout techniques, one with stack canaries and one was like heap relocation. Yeah, so how do you figure out what kind of variables do we care about relocating and stuff? So we define a thing called input channels. Basically, most overflow attacks are triggered with program input channels. These are typically memory vulnerable functions. And we define 6 types, prints, maps, scans, put, get, move, and copies. So mem copy, scanf, fgets. And we get attackers will manipulate the arguments of these input channel functions to trigger buffer overflows. And so what we do is we backslash these input channels to figure out what variables will be affecting them, and we encrypt and decrypt them. The only issue, the one thing important is that these are common ones. There are other ones in other benchmarks like Nginx have their own printfs or have their own mem copies, so you need to add them to the list. Now, for stack canaries, so the idea is that anytime a stack variable is being used by input channel, we move to the top of the function. If it overflows anything, it overflows upwards. And between each variable, we add stack canaries, which we have put a random value in, and we encrypt and decrypt them. So for example, this one, if var 2 and 3 are being used by input channels, we put them at the top, and we add canaries in between them. So before any input channel for a stack variable is used, we encrypt them again. Because if you have a very long call chain, you might be able to figure out the canary value eventually. So if we encrypt the value before the input channel, we can get a new value which the attacker will not know. And after that input channel, we decrypt it to make sure no overflow happens. Now for heap relocation is that in the heap, you cannot figure out where the variable, where the array or the thing will be allocated. So we can't add canaries. So a more easier method was to isolate these variables to a particular part of the heap. And so we make an isolated part of the heap. So if 4 and 6 are affected by input channels, we put it separately compared to 5. And the idea is that we make our custom memory allocation mostly. Basically, any variable affected by the input channels, we allocate a big chunk of memory ourselves. We analyze this beforehand, and then we would allocate stuff on that isolated part. If you're not affected by input channels, you can use the shared memory locations. And now anything in the isolated part needs encryption decryption because it can still overflow each other. So like 6 can overflow into 4. So in a real example, there's an input channel called str copy. It targets some input. So we move some input to the top of the stack. We add a canary with some random value, and then we encrypt it. And then if you, of course, re-randomize it again, in case it's a long call chain, which we put to get figured out. And then we encrypt it and then decrypt it to check for overflows. So this is a simple example to explain what happens. So when we validate a technique, we wanted to see how good is this conservative scheme of complete authentication. How good is PyTia compared to this conservative scheme? Do we actually reduce the overheads, or do we decrease the number of authentication? And how does it compare to DFI? And so the first thing we want to show you is that how many input channels we found in the program. So we found around 25,000 input channels across Spec and Nginx. 31.5% of them are prints, 65.9 are moving copies. In Nginx, what they do is they don't call it mem copy, they call it copy mem, but it's basically a defined version of mem copy. The other thing is that in LLVM, what happens that even if a thing is not some particular like function calls will actually call something called LLVM mem copy, which is just an interesting function, even though it's not from a mem copy function call as source code. So you need to take into account those ones also. The other thing is that branch protection. How many branches do we do well on? So our branch protection is around 92% compared to DFI's 86%. We fully protect 3 complete benchmarks compared to DFI 1. The issue with PyTia is that we cannot detect like field overflows. So if you have a struct and a bunch of fields in between them, if it overflows into the next field, we don't have a canary for that. If you overflow the entire struct, we should be fine in that case. DFI has issues with some C++ things, and so we take care of those ones. In terms of binary size, if you do all point authentication, it's like 21%. If you do PyTia's scheme, it's 10%. And if you do first complete point authentication is 47 compared to 13%, which actually decreases the number of point authentications by 4.25x. So in conclusion, PyTia has a compiler-guided defense framework with point authentication to tackle non-controlled attacks. It utilizes hardware components already available in ARM chips like Apple machines or Graviton. It's effective on pointer-intensive applications and C++ code. And it works on real-world attacks. So we have an example in the paper of Pro STPD using str and compare, which is a very common example. Our average overhead is 13% compared to a complete point authentication 47. And we secure like 5.6 million branches, which is actually around 30,000. Thank you.
Hi, Joey Rudick, UC San Diego. What's the memory usage overhead for SMalloc?
So for this one particularly, I think it's in the paper, but I think it's around like for the heap mostly like 20%. I think so. I think yeah.
Cool. Thanks.
Hi, thank you for the talk. Mohammed Ismail, I'm from Virginia Tech. I have a question regarding your functions that you added in. Is your framework flexible to add more functions, or is it?
Yes.
If I wanted to add more
Yes.
functions, would I have to do a lot of changes?
No, you wouldn't actually. So the idea is that once you know what functions you want, you can add it to like one of the function calls in our LLVM pass, and you can add more cases if you want. Yeah, we try to make it more robust because, of course, we have defined what we call input channels, but other people might define new ones. Yeah.
Oh, thank you.
Well, great work. I have a question about input channels that you provided in one of your slides. So if you can come to that
Yes,
one. Yeah, so that one. So here, right, why would I use your system rather than identifying this input channels, which are the non-secure version of the C functions, and replace those rather than, using an hardware-based compiler extended system that you like? What are the disadvantages there, replacing those with compiler support rather than, using your system?
Let me, I would say that because, you want, if you want to replace those functions for every single program, for every single Linux or machine, it'll take time. So having a compiler approach allows you to more generalize for any machine. And so until you can do that kind of case.
Okay, thank you.
For the questions, thank you, Sajid, for the. Okay, so the next paper is Everywhere All at Once, Co-location Attacks on Public Cloud. To present this work, we have Anish. He's a final year PhD student in computer science at the University of Illinois, Urbana-Champaign, advised by Professor Joseph Torrelas. His research is primarily focused on computer architecture, system security, and cloud computing, with a special interest in understanding and mitigating side channel threats in modern computer systems like clouds. Please.
Okay, thank you so much for the introduction. I'm very happy to be here to present our paper called Everywhere All at Once, Co-location Attacks on Public Cloud FAS. So microarchitectural side channel attacks have been around us for a long time, and they are practically everywhere in a modern processor. Fundamentally, these attacks exploit the shared resources between the attacker and the victim. Therefore, to actually pull off one of these attacks in a public cloud environment, the attacker needs to first find a way to achieve co-location with the victim on the same physical machine before one can extract information from the victim. However, how to achieve this co-location is often overlooked. Therefore, in this work, we focus on step one, the co-location, and we use production Google Cloud as an example. And I want to apologize for Google because they're a sponsor of the conference, I guess. So the product that I targeted is called CloudWang, which is a fully managed containerized environment that supports many computing paradigms like function as a service or FAS. So here is a very quick background introduction to what such an environment usually looks like. From high level, the developers develop some program and pack the program with the required libraries into a container image. Then they specify how much resource is going to be required by a single container instance, and then deploy the image as a service. After the deployment, the entire service is fully managed by the cloud vendor. For example, if the service takes an incoming request, the cloud vendor will automatically launch a container on one of the physical hosts to handle this request. And note that here, the selection of the physical host to run this container, namely the instance placement policy, is fully managed by the cloud vendor and is unknown to the user. In the future, if the service takes more requests, the cloud vendor will automatically scale out to launch new containers, potentially on different machines, to handle this new incoming request. And if any containers become idle, they are going to be terminated automatically by the cloud vendor. So the key takeaway here is that in such an environment, the container placement policy is fully managed by the cloud vendor, and the users do not know about that. Second, the container creation and destruction are automatically adapted to the service demand. So given this environment, achieving co-location is hard. Let's paint this picture. We have a large data center, and the victim is running on one of the physical hosts. As an unprivileged attacker, you do not really know on which machine the victim is running. So one potential strategy you can apply here is that you try to launch try to send many requests so that they are going to trigger many container launches, and they are going to hope that these containers can spread across many different physical hosts, and that can increase the chance of co-location. However, that's hard, because as I mentioned before, the attacker has no control, no knowledge of how containers are placed in the cloud. As a result, naively launching these containers often has a low chance of co-location. To overcome this challenge, here's our big idea. we want to have a way to fingerprint the underlying physical host. And this fingerprint can serve as a mostly unique identifier for the machine. With the fingerprint, we can then reverse engineer the placement behavior. For example, you can try a certain launching strategy and record the fingerprints of the physical host that run these containers. Then you can try a different launching strategy and compare how the Google Cloud is going to react to different strategies. So that's the idea. And here are the main contributions of this work. So first, we proposed a method that can generate accurate host fingerprint. Second, we have a way to validate the co-location very inexpensively at a large scale, which is important given how large data centers are. Finally, we used fingerprints to study how containers are scheduled in production Google Cloud, and we discovered an exploitable behavior. Exploiting that, we can achieve co-location with a high chance. So due to the time limit, I'm going to focus on the fingerprinting and the exploitable behavior part. Here's the basic insight of the fingerprinting. It's based on an insight that when a physical host boots up, the boot time of the physical host is likely to be unique within the data center due to the maintenance and hardware failure. As a result, our proposal here is to use the boot time as the fingerprint. However, you cannot directly grab the boot time from the host because everything is running in a software sandbox. So our second insight here is that you can bypass this software protection by using unprivileged instructions like RTTSC to directly interact with the underlying hardware to learn some information about the boot time. Here, the hardware part that we're interacting with is the timestamp counter, which has two useful properties. First, it's reset to 0 when the host boots up. Then it increments at a known fixed rate. Let's call it F. And the value of F is the same regardless of the CPU frequency scaling or power state. Given these two properties, we can then derive the boot time. To understand how, consider this timeline. At one point, the host boots up at an unknown time tboot. During the boot, the timestamp counter is reset to 0, and then it increments at a fixed rate. Sometime in the future, at time tq, attacker can use RTSC to read the value of the timestamp counter and derive that the host has been up for timestamp over F this amount of time. From there, you can easily derive the boot time to tq minus uptime, and that's our fingerprint. Next, the question that how do we actually validate the accuracy of the fingerprint? You are going to need some ground truth on whether a pair of containers are actually co-located on the same machine or not. Well, to do that, here's a very quick idea. You can take a pair of containers and you command them to put pressure on the shared resource at the same time. This shared resource can be cache or random generator, which is what we use. And if you see contention in both containers, then you know that they are co-located. Otherwise, they are not. While simple, this approach is not very scalable because it's going to require O(n)² pairwise tests to test n containers. And in the paper, we proposed a more scalable approach to validate co-location, which is assisted by the fingerprints. But nevertheless, we use this method to validate the accuracy. And here we are measuring two metrics. One is false positive, which is defined as for a pair of containers, if they have the same fingerprints but are actually not co-located, then that's a false positive. And false negative is the exact opposite. So under this, we performed the accuracy measurements in three Google Cloud data centers, and we repeat our measurements 5 times in each data center at different times of day and different days. So averaged across all these 15 measurements, we see 0 false negative rate and a very tiny false positive rate. And 14 out of these 15 measurements generate perfect fingerprints. So with these accurate fingerprints, we can now understand how containers are scheduled. And recall that the approach is to launch many containers and record the fingerprints of the hosts that run these containers. Here I'm going to summarize my observations. And here each circle represents a physical host. My first observation is that for containers that are launched by the same account, Google Cloud always prefers to schedule them to a very specific set of hosts. The reason why they are doing so is likely due to affinity scheduling. Basically, they want to group containers that may communicate with each other onto the same host to reduce the communication overhead. Our second observation here is that different accounts, they have different preferred hosts. As a result, if you just naively launch containers, you are not going to go beyond this preferred host, so the chance of co-location is going to be very small. Luckily, we found an exploitable behavior that can bypass this. Basically, you want to repeatedly launch containers. You want to launch some containers, wait for them to be terminated, and repeat the process again, and that can help attackers to occupy a large set of different physical hosts. The reason why this is happening, based on our reverse engineering, is that repeated container launches can trick Google Cloud to believe that the user has a high demand, thus triggering a load balancing behavior. And that's the behavior where we exploit it. To evaluate the efficacy of this strategy, in our evaluation, we use account 1 to represent the attacker who launches about 5,000 containers in the way that exploits this load balancing behavior. And as for the victim, we use 2 different victim accounts, and each account launches 100 victim containers. And we measure the victim coverage, which is the percentage of the victim instances that are actually co-located with the attacker. Here are the results. We conducted this measurement in 3 different regions and 3 repetitions in each region. For US East one, we have a coverage of near 100%, which is very high. And in the US Central one, we have slightly lowered coverage from 61% to 90%. The reason of the reduced coverage is likely due to the large size of the US Central one. And for the US West one, we have 100% coverage because that's the smallest data center we observed. And in terms of the attack cost, it costs you about $23 to $27 to perform the attack, which is quite cheap. So the takeaway from the evaluation is that with by exploiting this load balancing behavior, you can achieve high victim coverage with very low attack cost. So now to summarize, basically the main insight of our work is that you want to fingerprint the physical machine and use that to reverse engineer the instance placement policy. And in the paper, we discussed how you can generate accurate host fingerprint, how you can validate co-location inexpensively, and then we use fingerprints to discover an exploitable behavior of Google Cloud. Exploiting that, you get high coverage and low attack cost. Finally, this is our open source. So that's the whole talk. Thank you.
Hi, thank you for the talk. I'm curious to know whether or not your attack would be applicable on other architectures other than Intel, because RDTSC is an Intel architectures, but ARM, for example, does not, as far as I know, does not have an unprivileged timing kind of instruction that you can use. And the Graviton AWS servers use the ARM cores. Do you think your attack would also work on those or no?
So yeah, that's an interesting question. Does it apply to architecture other than x86? I did not try ARM. If they have this user space counter access, sure, the same method can be applied there. If not, we might need to find a different way. But even at this day, the most servers I saw on Google Cloud, they are still x86. Actually, Intel CPUs, like Skylake, Cascade Lake. So it applies there.
Unprivileged instruction to access. This is a necessity for your attack to succeed.
For this strategy, yes, because the user is like running as an unprivileged container. You cannot execute privileged instructions.
That makes sense. Okay, thank you.
Hi, thank you for talk. And on page 16, so how do you get the ground truth on page 16?
How do we get the ground truth?
Yes.
Page 16. Okay. Basically, if you take a pair of containers, you make them to put pressure on the shared resource. If they are actually co-located, you should see contention when they're accessing this shared resource. Does that make sense?
Oh, so if you detect 1, 2 machines access the shared result and the long latency, and you record it as a colon.
Yeah, for example, if you can ask 2 containers, both of them to put pressure, high pressure on the shared cache, and if you see tons of cache misses, then that's a strong signal of being co-located.
Oh.
The one we used actually is based on the random number generator. You're welcome to check out our paper for more details on that.
Okay.
Thank you.
Thank you.
Very interesting talk. So I have a question. So I feel like the collocation observation is very interesting. So I'm wondering if you can leverage those collocation observation to launch not only side channel attacks, but denial of service attack. Is that possible?
I think that's potentially possible because you can get a bunch of attacker containers onto the same host, and then you can command them all at the same time to stretch the cache or use tons of resources to degrade the performance of the victim service. I think that's possible, but we did not try that.
Thanks.
Since we are like 5 minutes out of time, we'll leave the rest of the questions for offline. So thank you, Dave.
Okay, thank you so much.
Thank you for attending.